Here's a quick video on the lab for tomorrow that we're going to look at using the FFT Analyzer on the scope. We'll start out with the basic sine wave, 1 volt RMS and 1 kilohertz. Now, one of the adjustments you may need to make is on your ARB generator. Now this description is in the handout. The handout is really two pieces, the basic lab and then a tutorial on doing the FFT. Alright, so we need to check if the ARB is set up properly in terms of its output impedance. Hit Shift Enter to go into the menus. Then we will press the right arrow button to go to the D menu or the system menu. Press the down button and you will see output termination. If I press the down button, you will see the parameter high Z. This means it's treating the output as a high impedance load. Or if you press to the right again, you will see 50 ohms. 50 ohms is convenient when you're working with a spectrum analyzer. For us, we want it to be high Z. So either press right to go to high Z or press left. Once you have high Z displayed, press enter and the data will be stored. Now you have set up the ARB to match the scope, which is a high impedance device. Now if I look at the display on the ARB, I have 1 kilohertz and I have 1 volt RMS. If I look at the numbers on the scope, I see 1 volt RMS and 1 kilohertz. So they are matching. If they do not match, check your probe settings. They might be adjusted to something other than 1-to-1, or call the instructor over and we'll figure it out. Alright, so now we have a 1 volt RMS signal that is at 1 kilohertz. Now we want to use the FFT function. The FFT function is under the math function. If we press math, we will see a new display displayed along with our sine wave. It's kind of the spiky down here, and then there's a mark up here. This is the FFT display. It is displaying amplitude in voltage versus frequency, just like a spectrum analyzer with some basic differences. In order to set up the FFT, press the settings button and you will see several controls. The two key controls are the center and the span. These are similar to the spectrum analyzer. We are going to set the center to 10 kilohertz and the span 20 kilohertz. So center. Go down to 10 kilohertz. Adjust it until it is 10 kilohertz. You can see that. And then the span we will set to be 20 kilohertz. Now we see our display. We see the time domain display of the scope and the frequency domain, amplitude versus frequency. Now this is not as clean of a display as the spectrum analyzer, and there's a few things you must do to clean it up. First thing, you'd like to see at least 5 cycles. 1, 2, 3, 4, 5. This will make for a cleaner display. Hopefully you can see that already. The spike is much more well defined, and that will help. Now we need to be able to determine what are the values on the spike display. So in order to do that, first we turn off the scope display because we don't want to get confused. So by pressing 1, the scope display goes away and we see just the spectrum display. Now remember, we set the center to be 10 kilohertz and the span to be 20 kilohertz. So 10 minus half the span is 0, and 10 plus half the span is 10 plus 10, or 20 kilohertz. So we're seeing a display from 0 to 20 kilohertz. And we see our spike here. Now we want to confirm that that spike is our 1 kilohertz signal and 1 volt RMS. Alright, this is how we do it. We press the cursor's key. When we press the cursor's key, you will see the bottom soft keys change, and we have X and Y cursors. The X is obviously for the horizontal display, the Y for the vertical. So we press X and then X1. When we change the knob, the rotational knob, you will see that number change, and you will see the dotted line of the cursor move. If I position that near my display, you will see at 1 kilohertz the dotted line or the cursor lines up with our spiked waveform. Now we will check the amplitude. Go to the Y mode, Y1, and we will dial this up until we have a reading. Now the reading at that point reads 0 dB. So how did our 1 volt RMS signal become 0 dB? For that, we need to do a little bit of chalkboard work. Okay, so a sine wave of 1 volt RMS and 1 kilohertz displays as 0 dB on the FFT Analyzer. If 0 dB equals 20 log V1 RMS over Vref, if VRMS equals 1 volt RMS for 0 dB, then 20 log of VR1 RMS over Vref equals 20 log of 1 or 0 dB. Therefore, Vref equals 1 volt RMS. So the FFT Analyzer is referenced to 1 volt RMS. If we would like to turn around the calculation, starting with the FFT dB reading, divide it by 20, raised to the power of 10, and that will equal the VRMS of our signal times 1 volt RMS. For example, we had 0 dB as our reading, divide by 20, still is 0, 10 to the 0 is 1, equals the volts in RMS, which is 1 volt RMS. So if you want to turn a dB reading into RMS, simply use this formula. If you want to turn a voltage into dB reading, use this equation, 20 log VRMS for Vref. Now this only applies to our analyzer and its reference of 1 volt RMS. Okay, back to the unit. Now we can check to confirm our calculations. For example, we will now change the frequency of our signal by 1 kilohertz. So if we change from 1 kilohertz to 2 kilohertz, we will see the spike move to the right. And for example, if we're at 5 kilohertz, we see the spike has moved halfway towards 10 kilohertz. In fact, we can easily confirm the 10 kilohertz mark. So with a 10 kilohertz setting, we see the display is in the middle of the screen, which matches up with our settings, which was 10 kilohertz in the center and a 20 kilohertz span. If we want to confirm that, we can press the cursors, the X, dial our cursor over until we get to the center, and we know that point is going to be equal to 10 kilohertz, the X1 indicator. X2 is just another cursor. We can move out of the way if we want, but or you can put it at 0 if you want to identify the difference between the two cursors. Alright, so now we've confirmed the frequency reading on the horizontal scale. Now we need to confirm the vertical scale. So we're going to change this signal, the Y signal, to be equal to minus 10 dB. So Y1, dial it down to minus 10 dB. I won't do the calculation here, But if you drop a voltage by dB, in this case minus 10 dB, if you stick that into your formula, minus 10 divided by 20 raised to the power of 10, you will get a voltage of 0.316 volts. So let's adjust our amplitude on our unit. So we are now at 1 volt RMS, so we're going to type in 0.316 volts RMS. So we press the green button for enter number, decimal 316 volts RMS. And we see that exactly where our 10 dB cursor was placed is our signal. So now we have confirmed that we have frequency and volts RMS related to 1 volt RMS on our FFT display. Now let's return our signal to 1 kilohertz, and you can see the display move. We'll return our level to 1 volt RMS, and we're back to where we started. Now we can look at other waveforms and determine their FFT display. We can easily check square waves, triangle waves, and ramp waveforms. These are very convenient because we have knowledge of them. So for a square wave, we expect, and we see the harmonics, the odd harmonics. Fundamental, 3rd, 5th, 7th, 9th, 11th, 13th, 15th, 17th, 19th. The 19th harmonic is 19 times the fundamental, which is 1 kilohertz, or 19 kilohertz, as we expected. If we select triangle wave, we expect to see fewer levels or a lower level of harmonics. And that is what we see. We still see all the odd harmonics, but they are much reduced. If we switch over to the ramp function, the ramp, if you remember, has both odd and even harmonics. And so we see the even harmonics, 2, 4, 6, 8, 10, 12, 14, 16, 18, and even a little bit of the 20th. So that's our FFT Analyzer in a nutshell. You can read off the individual values by dialing the frequency using the cursors and picking out the particular dB level. So here's the second harmonic. It's occurring at 2 kilohertz, which we see. We switch over to the Y and adjust the level, and it has a level of about minus 8.13 dB. Now that's reference to 1 volt RMS. Alright, so that's the setup for the lab and using the FFT Analyzer. Now you can return to the front page and start with waveforms 3 and 4 are the pulse waveforms.